Hello, and welcome to my talk on natural language modeling with Amazon SageMaker and BlazingText algorithm. My name is Denis Batalov, and you can follow me on Twitter at the handle shown. I'm a worldwide tech leader in artificial intelligence and machine learning for Amazon Web Services. I do have a PhD in this field, but I'm hoping to convince you that you don't need a machine learning degree to take advantage of the tooling that AWS has put at your disposal. In this talk, we're going to pick a natural language to work with, purposefully a foreign language, likely unfamiliar to you, and apply machine learning to create some magic. We will use the language of Georgia. No, not the US state of Georgia, but the Republic of Georgia, a small and beautiful mountainous country with an ancient history located between Turkey and Russia. The reason I picked Georgian language is because, like most of you, I was not familiar with it, did not know the writing system, and I wanted to apply known machine learning techniques, such as the BlazingText built-in algorithm into SageMaker, to see how machine can automatically discover word relationships in a language unknown to me. What's cool about today's talk is that you can apply the same techniques with ease to your favorite natural language out there. Here's what I expect you to know already. First, you already understand the fundamentals of machine learning and deep learning. Second, you have an understanding of the problem space of natural language processing or information retrieval, i.e. search. And third, I expect you to be familiar with some AWS services already, though not necessarily SageMaker. And knowledge of Python and Jupyter would help you understand the demo faster, but strictly speaking are not required. Once you know some programming language, it's usually easy enough to dabble in another. Well, in order to get the magic, we need to introduce the concepts of word embedding and word-to-vec algorithm, and then review the tooling that we're going to use, namely the Amazon SageMaker service and the built-in BlazingText algorithm. That will give us a solid foundation to then spend the bulk of the talk in the demo. So let's dive right into word embedding. Natural language texts consist of words, and so we need to represent individual words or sentences and collections of words in some way. Couldn't we just use strings containing the words? First of all, words have different length, and even written representations differ dramatically from language to language, with complications of capitalization, diacritics, etc. on top of that. More importantly, many machine learning techniques require numeric rather than text input. So our first idea is to simply associate numeric labels with words. For example, here we have a phrase to be or not to be. There are only 4 unique words in the corresponding vocabulary, so we can just assign numbers 0 to 3. Now we can effectively replace the phrase by a sequence of numbers. This representation is not ideal for many reasons. Numeric labels inadvertently introduce random relationships like less than or greater than, and even distance. Is it fair to say that the word not is somehow further away from to than the word be? Is not bigger than or? Our next idea is to use a vector instead of a single number. The typical approach is to use something like one-hot encoding. Here, each word acts as an index into a vector of all zeros with only a single element set to 1, the one that corresponds to the word. Here, you see the vectors that correspond to each of the words in the phrase. And we can even sum all the vectors together to have a single vector that represents the entire phrase. You'll notice that the same vector would be obtained regardless of the order of words, and that is why such simplified document representations are often called bag of words. You can probably start to guess what the problems are with one-hot encoding. In this example, our vocabulary is only 4 words, but languages typically have hundreds of thousands of words. Imagine very long vectors with all zeros and only a single one. The dimensionality is huge, but the vectors are very sparse. Now, suppose instead we reformulated the problem as predicting words that surround other words. In other words, we're predicting the context of a word. In this example, we're trying to predict the context around Tom Hanks, where Tom Hanks is effectively treated as a single semantic token. What is the probability that somewhere around Tom Hanks we would find words great and actor? Presumably, the probability should be much higher than finding quantitative easing next to him. Imagine now that we have put together a simple, fully connected network where for input it receives one of, say, 10,000 words in a vocabulary we choose. Since we want to output the probabilities for each of the 10,000 words to be next to the input word, our output layer needs 10,000 units. We then throw in a hidden layer of, say, 300 units. We train the neural network on our texts, extracting context words in a window of, say, 5 words surrounding each word, and apply a softmax function to amplify words with the largest probabilities. After training such a network, we can now quickly compute a denser output vector for a sparse input vector. In some ways, you can also view this output vector as representing the input word by emphasizing the words it is related to. The problem with such a simplistic approach is that we still have many weights to train, exactly 6 million weights in this case. Note also that the output vectors have the same dimensionality of 10,000. What if we reduce the output dimension and effectively compute a dense vector representation for every word? This is where we come to the word-to-vec algorithm. It was conceived of by Thomas Mikolov and colleagues with the ideas outlined in 2013 paper. The dimensionality of the output vector is a parameter you choose, and this is why we're said to be embedding a higher dimensional object, one hot encoded word in this case, into a smaller dimensional space, turning a sparse vector into a much denser representation. Once this representation is computed, we simply convert every word into a vector in an n-dimensional space. In the end, words that appear in similar contexts would likely be mapped to similar vectors. Words close to each other in the vector space are likely to also be close in meaning, since they tend to appear in similar contexts. And this is where we're getting closer to the magic. A machine learning system automatically discovering words that appear to have similar meaning. In theory, we also expect certain vector relationships to hold. This does not have to be exact and depends heavily on the training corpus of text. But we can hope to discover word relationships with transitive properties as shown on the slide. For example, if we take a vector that corresponds to the word king and subtract the vector that corresponds to man, we would presumably obtain a vector that corresponds to the concept of royalty. And so, if we now add the vector for woman, we expect to be getting something close to the vector that represents queen. While new ways of modeling a language constantly appear, you may have heard about BERT, Roberta, or even GPT-2, the concept of embedding is quite fundamental to the machine learning. Moreover, it generalizes to the notion of arbitrary object embedding, i.e. translating a potentially complex data structure into a vector. For example, you can represent users and items in this way in order to build a recommender system. So, imagine we have computed a word embedding for English, mapping each word to, say, a 100-dimensional vector. How can we visualize this result, ideally in a 2-dimensional picture? This is where we can use another trick of the trade and use the so-called TSNE plot, which computes another embedding. Imagine that. But now embedding 100-dimensional vectors into just 2 dimensions, while at the same time trying to preserve clustering properties of vectors. Let's look at some clusters. It may be hard to see, so I increase the size on the right. Here, you clearly see words that relate to human life and kinship. Over here, the algorithm discovered the concept of countries. And this cluster clearly corresponds to concepts of land and water meeting together. Very interesting indeed. Okay, but remember that we want to get to doing that for Georgian language, so it's time for us to get familiar with the tooling. Let me start by giving a quick introduction to Amazon SageMaker. While SageMaker is a very versatile service, I want to make sure to put it in context of the entire AI ML offering from AWS. Well, there's quite a few things shown in the slide with respect to the stack, so let's parse this out. We have to take a layered approach to offering our machine learning services because of various skill level or various comfort level that machine learning practitioners have out there. Our approach is to support machine learning practitioners of all levels of skills and experience. So at the very bottom, we have the so-called machine learning frameworks and infrastructure layer. In other words, if all you need is some powerful GPU that you would like to launch and start building code right on top of this machine without the need for a lot of tooling, then this layer is right for you. You're able to write low-level code or use one of the standard frameworks like TensorFlow, MXNet, or PyTorch. And here, we give you an ability to use the so-called Deep Learning AMI or Amazon Machine Image. So launch an instance with the right kind of hardware with this image, and off you go. And we even have features like elastic inference that allows you to utilize a portion of GPU, exactly the amount of GPU that you really need. And then, on the other end of the spectrum, at the top layer, we have the so-called AI services. This is where the models have already been built for you for the most part. You don't really need to have any data to bring and to train the machine learning models with that data here. Everything is available in just a call of the API. So for example, if you want to label a particular image, to understand what's in the image, you can use recognition. Textract is about extracting text from images of documents. And if you want to generate speech out of plain text, you can use Poly. Want to do machine translation of text? You have Amazon Translate for that. You can analyze text with Comprehend and build chatbots with Lex. And on the right-hand side of the top layer, you see services such as Forecast and Personalize. These are slightly different from the rest in that the tools allow you to train a model based on your own data. But the exact algorithms and the exact customizations are already built in, and you can use features like AutoML to automatically choose a lot of things for you. So in that sense, the services are much easier to use. You don't really need to have a machine learning background to employ these services and to take advantage of that functionality. And of course, today we're actually going to focus on this middle layer here, which is the Amazon SageMaker. And this is our platform that includes all kinds of capabilities. I will show you some in this talk, and then there are many others to discover later on, such as labeling the data by using ground truth functionality of SageMaker, or even doing things like reinforcement learning, perhaps with DeepRacer. Amazon SageMaker takes care of all the steps shown here that a machine learning practitioner typically needs to be able to do, starting with collecting and preparing data, choosing the right algorithm, optimizing it, and then launching the training at scale, perhaps on a cluster of machines, ultimately leading to deploying these models into production, where you need to manage, monitor, and scale these models. We offer pre-built notebooks to solve common problems, and those examples are available right within SageMaker environment, so a machine learning developer can take a particular notebook, customize it to their own use case, and proceed with training and deployment. Once you settled in on an approach and obtained a training dataset, you need to choose the right kind of algorithm. And SageMaker offers a variety of algorithms built in that cover a broad range of use cases, starting with supervised learning, where you have very popular algorithms such as XGBoost for decision trees or factorization machines for recommendations, well-understood linear algorithms, and k-nearest neighbor. For unsupervised learning, you can use k-means for clustering, principal component analysis, and random cut forest for anomaly detection. For image-based data, you can choose built-in image classification or object detection. And for text and natural language processing, you can use LDA or latent Dirichlet allocation, neural topic modeling, sequence to sequence, and BlazingText, which is our efficient implementation of Word2Vec we will use in this talk. Once you've chosen your algorithm, it's time to initiate the training. As you will see in the demo, once we specify the number of machines we want to run training on, we can kick it off in one line of Python code using the SageMaker SDK. The way SageMaker handles it is that for every popular framework that it supports, as well as the built-in algorithm, it uses a Docker container that's designed for that specific algorithm and designed to support that particular framework. What you do when executing the training is selecting the right container and then providing the data in the form of, say, file in simple storage service. And what SageMaker will do is launch a cluster of the training machines and then read in the training data into those machines from S3, perform distributed training. If it's distributed, you may also run it on a single machine, of course, and then output the resulting model back to S3. Great, but what if you need to optimize the model? What if the model performance is not sufficient? Well, in this case, there are various model optimization opportunities for you. And number one is called automatic model tuning or hyperparameter optimization. You see, for any algorithm that's out there, there's usually a bunch of parameters that control its behavior. And often machine learning practitioners are left in the dark as to which values to supply for these parameters. But don't worry, because automatic model tuning comes to the rescue. The reality is that even machine learning practitioners themselves, experienced ones, often don't know what to do in this case. And they rely on automatic model tuning to explore the parameter space and pick the right parameter set for you. SageMaker allows you to do that by kicking off the so-called hyperparameter optimization job, and you specify how many machines this needs to run on to control the costs, and ultimately it helps you pick the right model. Besides automatic model tuning, SageMaker also offers you an ability to compile your model. So this is called Amazon SageMaker Neo. We support multiple popular frameworks, such as the ones shown on the left, and you're able to target the compilation to one of the hardware choices on the right. And as a result of this compilation, your model might actually be smaller in size and run faster and be more performant. Once we've obtained the model that we actually like, that has the right kind of accuracy, we need to deploy it to production. And of course, SageMaker helps you in this regard as well. We will see that literally in one line of Python code, you can take the trained model and deploy it to a production endpoint that you can then manage and easily scale like everything with Amazon Web Services. Now that we've talked through the basics of the Amazon SageMaker service, we're ready to jump into the details of the BlazingText algorithm that we're going to be using during our demo. So first of all, this algorithm was published in 2017 by a couple of Amazonians with a paper shown here. And the key thing to know about BlazingText is that it provides a highly optimized implementation of Word2Vec and text classification algorithms. The other important thing is that it offers an implementation of a supervised multi-class, multi-label text classification algorithm, extending the fast text algorithm implementation using the GPU acceleration with custom CUDA kernels, but also relying on multiple CPUs for certain modes of operating this algorithm. And using BlazingText, because of its performance, you can train a model on more than 1 billion words in a couple of minutes using a multi-core CPU or GPU. And you can achieve performance on par with the state-of-the-art deep learning text classification algorithms out there. Here are some additional performance characteristics that you can note. You can run the algorithm in many different modes, and for example, on a single CPU, on multiple CPUs, on a single GPU taking advantage of several cores, and so on and so forth. So in this particular demo for us, we're going to use distributed training. In our demo, we're going to use BlazingText on multiple CPUs. But even within a single CPU, BlazingText takes certain steps to optimize its performance. So for example, in a kind of standard implementation that you're seeing on the left side of this diagram, we have BLAS1 type operations where we're not really sharing the negative samples that the algorithm is using to train its weights or train its vectors. Whereas the BlazingText algorithm actually relies on the MKL optimizations in Intel to perform BLAS level 2 operations, and those become more efficient even when running the algorithm within a single CPU. Over here, you're seeing throughput characteristics that BlazingText shows. On the right-hand corner, you see the implementation of fast text, sort of what's been published out there. And because fast text is not able to be distributed on multiple CPUs or GPUs, we're running it for these benchmarking on a single machine. Now, you can compare and contrast the performance when you look at the left-hand side, where the algorithm has been run on multiple or multi-core GPU machines. And in the middle section, well, you see the yellow bars, we have performed the batch skipgram benchmarking. And again, here you're seeing the results of running the algorithm in a distributed fashion on multiple CPUs. But of course, throughput is not sufficient for us to pick an algorithm or to rely on solely, because we also need to consider accuracy and cost. And in this diagram, you see a comparison of fast text and BlazingText. The way to parse out this diagram is as follows. On the left-hand side, you see the accuracy. The accuracy using the standard benchmark, using human kind of ground truth data on a standard data set. And in the horizontal axis, you see the cost of running the corresponding benchmarks. Now, the bubbles and the bubble sizes correspond to the amount of throughput that you can achieve with a particular run of the algorithm, given the hardware choices that are assigned and shown in the box next to the bubbles. And the ordinal numbers inside the bubbles in this case don't matter. These are just sequential numbers. But what I would like to draw your attention to is the kind of big yellow bubble in the top left corner, I believe number 8. This is running on a P3 2x large machine, the Volta GPU machine. And contrast this perhaps with a smaller green bubble to the right, comparing BlazingText with fast text. And you can see that in terms of cost, the BlazingText here is more performant, achieving kind of higher or similar accuracy at lower cost and with a much higher throughput. So clearly a win for everyone. And of course, you can also look at other possibilities here. You always need to know the details of what is the data set that you're running on, what type of algorithm you're choosing, what type of cost and performance characteristics you're after, and whether the accuracy is absolute requirement, which actually in word embeddings is not. And if you also take a careful look at the accuracy here, the numbers are not so dramatically different. The axis is sort of just showing you a window within kind of a small range of accuracies. So hopefully this gives you an idea of both throughput and performance of BlazingText algorithm. And this is our cue to actually jump into the demo. And this is how you'd spell or pronounce demo in Georgian, as it turns out. You can actually find out the sample notebook and additional information at the GitHub link that you're seeing on your screen. Okay, so what you're seeing here is the AWS Management Console. And I expect that you've seen this before, but just in case, I want to highlight the key important things here. So first of all, it's the region on the right. I chose to operate in the Ohio region. And then, of course, it's the choice of the service that you would like to use. If we scroll down, we see many, many services that are available for us. And of course, we're most interested in machine learning, and specifically Amazon SageMaker. So I'm going to click on Amazon SageMaker to open the SageMaker console. On the left-hand side, you see the navigation bar consisting of many aspects of SageMaker. So first of all, you see the dashboard. Great. We have ground truth. I've mentioned it briefly, but this is about labeling your data using a pool of workers, either public workers in Amazon Mechanical Turk or in a private labeling workforce that you can set up. There's also the notebook section. This is where we start a Jupyter notebook, our environment within which we're going to demonstrate the capabilities of SageMaker, type in some code, execute, and this is what we're going to do for the demo. And then, of course, there's the training section. This is where you'll see all the training jobs kicked off, and you can observe and monitor them and get the results. And finally, when you're ready to deploy the models, you can look into the inference section, look at the models that have been built already, look at endpoints and their configurations, and so on and so forth. And all of this we'll see in the demo. So first things first, let's click on the Notebook Instances section. What you see here are a couple of notebooks that I've set up, and one is already shown as being in service, reInvent 2019. This is the one that I will use to demonstrate everything today. You can create your own new notebook by clicking on Create Notebook Instance. You can choose the instance type, configure some other parameters, and shortly it will be available in a similar fashion, in service and ready to go. There are two options for us to open Jupyter or Jupyter Lab environments. Jupyter is the older kind of user interface, whereas Jupyter Labs is the newer user interface. Both are available for you. I will click on the Jupyter Labs, and in fact, I already have Jupyter Labs open for me and the other tab. What you see in the Jupyter Labs environment is a section on the left showing you the files that are available in a current working directory, and in a tab here, the contents of the so-called Jupyter Notebook. And of course, for us, we're focusing on word embeddings for Georgian language, and that's what this notebook is all about. Again, if you want a copy of this notebook, I pointed to a GitHub repository earlier on. This is where you can get the contents and the copy of that notebook for yourself, so you can customize it and maybe even try for a different language. What do you see in the notebook? Well, first of all, obviously we see some text and descriptions. And the great thing about Jupyter is it allows us to mix descriptions and text annotations with the actual code that we can run right inside the browser environment. So you can read the detailed instructions here, and you can see when I select something on the left, there's a blue bar that appears. That is selecting the top cell, which is the textual cell. Of course, nothing to run here. We just are interested in reading and maybe formatting that cell. And for this demo, the real first step that we need to do is actually obtain a large amount of Georgian text, a corpus of Georgian text, so we can train and compute those vectors. Where can we get those? One great source, of course, is Wikipedia. We know that there are Wikipedia available in many different languages, including Georgian, and you can look at the so-called Wikipedia dump and download the entire contents of the Georgian language Wikipedia to the machine for analysis. And that's exactly what we're doing here in step 1. So for me to do this, I'll select this cell. You see the blue bar on the left, and I will just press Shift-Enter to execute this cell. And of course, as we're running it, it's not so much Python code, but actually we're just shelling out and getting a particular file compressed, and it's being downloaded in front of our eyes. We would be ready to go once it downloads. What is this file? Well, it contains the contents of Wikipedia articles in a particular XML format. And XML is not what we need for this exercise. We actually prefer to get the plain text extracted out of Wikipedia. And so we do have a special tool that was built by Giuseppe Attardi and co-contributors. And we can download that tool from GitHub as well. And this is what I'm doing right here. The tool is called Wiki Extractor. So when we're going to run that tool over the entire contents of Georgian Wikipedia, it's going to parse every single article, extract as much plain text as it can, and then we may need to do some additional post-processing steps. So here, the Wikipedia has been downloaded. It will appear here And we're now ready to download the wiki extractor. It's just a small script. And we're now ready to run it on the contents of the Wikipedia. I've already done it. It takes some minutes, and therefore, to simplify the demonstration, we'll just extract it to a different folder. So extracted-ka-temp. And again, press Shift-Enter to run the script. You could see the first few lines of this extracted text. So it's doing something useful. Now, like I said, it will take some minutes. Therefore, I will stop by pressing I twice to interrupt the kernel and move on to the following cell. In this next cell, we're doing a little bit more additional pre-processing by eliminating some XML tags that are left over. And it will take some time to do that as well. And once it's done, you see every time a cell is finished executing, the number turns into, the asterisk turns into a number, and that means we're finished. Now let's look at the first few lines of this large single text file, KA corpus. KA is actually the language code of the Georgian language. In Georgian, the language is not called Georgian. It has its own name. And Georgia as a country is called Sakartvelo, not actually Georgia. OK, so we're ready to move on to SageMaker part. The first thing that we're going to attempt to do is set up an execution role, create a SageMaker session, point to the default bucket. The bucket that SageMaker uses in Simple Storage Service need to reside in the same region as we're running SageMaker in. So we're currently running in Ohio, or US East 2, and therefore the bucket that you use needs to be in US East 2. But if you just use default bucket, you get the right bucket for you automatically. And here's the bucket name, SageMaker-US East-2, and this is my account ID. Next, we need to point to where the training data resides, right? And in fact, we need to upload that training data to the S3 bucket. Currently, that text corpus is sitting right on our local notebook machine, but training happens asynchronously on a different cluster of machines in the cloud, and therefore we need to put it into S3. So we'll execute this cell. That will result in uploading this large textual corpus into S3. We also configure the output location for where the model needs to be deposited after the training is finished. And we're ready to go. OK, you can read the description here on your own. We've already talked about the details of BlazingText. We're just really eager to kick off training. And here's what we need to do. Well, we need to know the region that we're going to run the training in. And based on the region, remember I talked about Docker and Docker containers used for training and deployment? Well, we're going to need to point to a Docker image that is corresponding to the region and to the algorithm that we care about, which is BlazingText. So effectively, if I get the region and I get the container, I see that I'm getting the container in US East 2, and that container corresponds to the latest implementation of BlazingText, which is exactly what we want. The next thing that happens is a configuration of an estimator. And in SageMaker, an estimator is an abstraction that is used for training any kind of machine learning model using any kind of built-in algorithm or framework that you use. And so for the estimator abstraction, we need to supply the container we're going to use, the role we created earlier. We need to decide on the training cluster size. In this case, we're picking C4 2x large, and in fact, we're going to run it on 4 machines. We need to decide on the volume size of each one of these machines. This is in gigabytes, 5 gigabytes. We need to supply the maximum time that a training is going to run. This is just a limit to help us control the costs if the training for some reason takes too long. And in fact, in this case, we're going to be done much before this timeout. And we're choosing a file input mode, which means the entire copy of the training data will be placed into the machine that's running the training. And we're, of course, supplying the S3 output location of where the model is going to reside. Now, besides configuring the estimator, the next thing we need to do is specify the so-called hyperparameters. Now, remember when we talked about automatic model tuning? This is the feature of SageMaker that helps you automatically decide what the right set of hyperparameters is. Now, in this case, for the purposes of the demo, we're going to supply those parameters manually, relying on kind of my experience perhaps or my experimentation. But in the most general case, when in doubt, rely on automatic model tuning, because the reality is that even experienced machine learning practitioners often don't know what the right set is. So the first thing that we're supplying is the so-called batch skipgram. This is the mode in which the algorithm is running. There are a number of different modes, such as continuous back of words and so on. It's beyond the scope of this talk to kind of cover this, so I refer you to the algorithm documentation to understand how the different modes operate. We're choosing batch skipgram because that's the one that actually allows us to distribute training across multiple CPU machines. The next parameter is the number of epochs. Generally speaking, the more epochs you provide, that means the more passes over the training data the algorithm will do, the more accurate the results will be. But of course, at some point, it's not going to help any further, right? The accuracy will stop and maybe even decrease over time. So finding the optimal amount is also a bit tricky. And again, I would refer you or propose that you use automatic model tuning to decide what the right number here is. Then we have min count. Min count refers to the minimum number of times that a word needs to appear in the corpus for it to be included in training. So if there's some rare word that only appears a few times, less than 5 in this case, then vectors for it will not be computed. It's just deemed to not be interesting enough. Again, and totally configurable by you. There is various additional attributes, parameters on sampling threshold, the learning rate, which is typical of many machine learning algorithms, how fast you adjust the weights towards the target that you're seeing. An interesting one here is a window size. Window size refers to the number of words that surround your current word, right? And you're defining what it means for a context around this word to be, right? So we're saying only 5 words around a particular target word is our context. Then the next parameter is vector dimension. This is important. Remember that if we have 10,000 words in a vocabulary, then our dimensionality in the one-hot encoding is 10,000. We clearly want to reduce that dramatically. And of course, in any real language, like I said, there will be hundreds of thousands of words potentially. But we're embedding all those words in only 100-dimensional space. So that's cool. We're creating dense 100-dimensional vectors. And finally, there is something called negative samples. This is the key insight in how the word-to-vec algorithm functions by using negative examples during training and thus reducing the complexity of training and reducing the number of parameters that actually need to adjust on every single kind of backpropagation pass. And then batch size, there's some rule of thumb which makes batch size depend on the window size, and you see here kind of a suggestion. So if we picked window size to be 5, based on that suggestion, 11 is a reasonable choice for batch skipgram. And we're setting the other parameters to false because they're relevant to the way we're running the algorithm. And we're basically ready to go. Once these hyperparameters are set, we're ready to provide the input training channel for our algorithm. And then you could see that kicking off training is accomplished in a single line of code right here. Right? We're saying use this as the training data, and fit meaning train the model. Now, the fit function is an abstraction. It's used for both supervised and unsupervised learning models alike, and therefore, we're not really fitting something to some ground truth at the moment. Instead, we're computing the vectors based on the context observed in the natural language. Now, it will take several tens of minutes, let's say, potentially, to run the training. And therefore, I'm not going to kick it off in front of you. This shows you the log of an existing training. And you can see that SageMaker includes the output and the progress of that training. And once it's done, the cool thing is that SageMaker shows you how many billable seconds that training took. Remember, we ran it on a cluster of 4 machines, but you're only paying for just over 1,000 seconds of billable compute time. And SageMaker automatically shuts down the cluster, and you don't need to worry about a thing afterwards. Once the training is finished, your machine learning model is saved into S3 and is available for you to use. Once we're done, we're ready to deploy that trained model. And you can see again, it's a single line of code where we take the model, we use the deploy operation, we supply the instance count and the instance type. So we're going to create an endpoint backed by a single instance that we're going to run evaluations against. And if you need to, you can configure autoscaling later, but what we're doing here is creating a live real-time endpoint against which we can run our evaluations. All right, cool. So let's see what these vectors are, the ones that were computed as a result of that model. I've put together a certain number of words in Georgian, right? So this is roughly how they're pronounced. Say tsigny is a book, chai is tea, and so on and so forth. So I've created a payload out of those words, and I am calling the predict method of this endpoint that I created earlier, and I get back the vectors. So let's execute that. So you see that I should have, since I have 7 words, I should have 7 100-dimensional vectors, and these are the elements of these vectors kind of printed here in front of me. Okay, great, but these vectors are just numbers. The key insight is that these vectors are used then in other kind of machine learning steps where you can then decide perhaps to train a classifier, or you're replacing the word itself with a 100-dimensional vector. But what's interesting is we can also look at the perhaps distances between these vectors to see if there are certain similarities that SageMaker or BlazingText discovered in those words. So if I run the next cell, what you're seeing is the computed distance between the words book and tea, and it's about 5. Okay, 5 units again. Keep in mind that we're dealing with a new kind of embedded 100-dimensional space. We don't really know the parameters of that space. So the absolute value seen here is probably not so important. But at the same time, we see that the words ahali and zveli, which refer to old and new, they're closer to each other than book and tea. Okay, well, that's something. We also see that there are numbers. Erti stands for 1, and ori means 2, whereas orive means both. And so it's natural that numbers are used in a similar contexts and therefore should be closer to each other in this vector space. And you could see that, for example, 1 and 2 are definitely very close. Okay, cool. That's just random kind of sampling, looking at some of these results. But what about this nice visualization that you've seen for English earlier? We should be able to get the same thing here for Georgian. And so let's do that. For this, I will again use the so-called TSNE plot, where we're embedding a 100-dimensional space into just 2 dimensions. So for that, I need to download the model that is sitting in S3. And in case of Word2Vec, the model is actually, as shown here, compressed, consists of 2 files, the vectors bin and vectors.txt. So at the end of the day, the result of this is just looking up vectors for words. So we're unzipping the results. And then moving on to plotting the TSNE plot for the top 400 words in the Georgian language in this particular corpus. So here you see the output of all these words. I have no idea what these words are, and this is what's great about it, that you can take a language that you don't have any understanding, any insight of, apply machine learning, and get some interesting results. So let me scroll past that. And now I'm going to use the TSNE functionality in scikit-learn manifold library. Will take some time to execute. Now it's done, and we're ready to use the matplotlib library to show the resulting plot. Again, this takes a little bit of time to generate, but there it is. Okay, great. What can I glean out of this? Well, some things are sort of obvious. Right, if we look at some obvious clusters that show up, we see numbers. That makes a lot of sense, regardless of the language. We see years. But we see other clusters of words. And of course, we need to understand what these words are. We need to translate them, perhaps, to figure out if the resulting clusters are meaningful enough. And depending on the TSNE plot that is generated, you may find observations that I list here. So often the word for 1 and the word for 2, right? These are Georgian kind of numbers, but spelled out in words, and both, which is Orive as well, is close to each other. I've already mentioned Ahalidzveli, and Wikipedia being Wikipedia. Of course, there's a lot of historical articles in there, and so it's not surprising that we're seeing the word for Roman and the word for empire kind of appear in a similar context. And of course, as usual, when you're done with something, we don't need that runtime endpoint anymore. We don't need to have it live and ready to go. We want to shut it down and stop consuming resources. So don't forget to clean up and execute this cell. So like I was saying, depending on how you run the TSNE plot, depending on which words were chosen, you may have a slightly different looking plot. And therefore, I've taken one example here just to show you some of the clusters that I've seen in the past. And so one of these examples is exactly the numerals, or, ert, orive. You can see them close together. Another example is the same Ahalidzveli, the new and old. And finally, it's the same Roman and empire appearing as a cluster in another part of the plot. So run this on your own data set. Use a translator to figure out what these words mean. and see if you can get a sense of what each cluster corresponds to, as you see in the TS&E plot. And that really completes my demo today. So thanks a lot, folks. I hope you've learned something interesting today, where we've taken a completely new language that most likely you've never seen, you've never heard of even, and we've been able to download the Wikipedia contents, create a plain text corpus of it, and run SageMaker BlazingText to extract some semantic meaning and gain some insight into the language. I hope this talk today spurred your interest in SageMaker and your ability to perhaps take this and apply it to a language of your choice. Thanks a lot, folks.